Hello, in this lecture, we are going to discuss the sequence which generates the constant E. Okay, this is an important topic, so just pay attention to this. Okay, okay. So we know that we were discussing in the series of basic real analysis sequences, and there are some sequences which generate whose limit of some sequences generate important constants like E. Okay, so just consider this sequence. Just consider this sequence. Okay, just consider the sequence xn. Okay, and just think that for all n greater than equals to 2, this will be less than 1. So we can expand this binomially. We can expand using binomial theorem. We can expand it using binomial theorem. So let us try to do that. So if I do that, this xn would come out as 1 plus n into n minus 1 upon 2 factorial 1 upon n square, and last would be ncn raised and this 1 upon n raised to power 0. So basically this is what? This is nc2. This is what? This is nc1. So what I can do, I can write this xn simply as 1 plus summation k equals to 1 to n nck n factorial divided, this n raised to power minus of k. Okay, so instead of writing 1 upon n square and all those things, I've just written n raised to power minus of k. Now, you know that this nck can be again written as n factorial upon n minus k factorial, and this is k factorial, and this n minus k factorial which cancels this would give you what? Would it certainly give you n into n minus 1 dash 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 n minus k plus 1, and then you'll have this n minus k factorial here divided by n minus k factorial. This gets cancelled and you have this k factorial left here. So basically this, when solved, you can write this xn equals to 1 plus sums k equals to 1 to n, and this nck would give you n into n minus 1 dash 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 n minus k plus 1. So I would write n minus k minus, fine, divided by n raised to power k. Now just think about this. What you can do, you can just supply these. How many number of terms are here? There are k terms here because this is k minus 1. It starts from 0. This is n minus 0. Just think about this. 0, 1, and k minus 1. So these are in totality k terms. And it is being divided by n raised to power k. So this is n multiplied k times. So basically, what I can do, I can supply this n individually inside all these brackets. So this xn would be equals to 1 plus summation k equals to 1 to n, and you will get simply 1 here, and then you will have, okay, I forgot some k factorial would also be here. So k factorial will also be here. So 1 upon k factorial will be there, and then you will have this 1 times 1 minus 1 upon n. See, this would be 1 minus 1 upon n. If n is supplied here, then n minus 2. So this will be 1 minus 2 upon n dash 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 1 minus of k minus 1 upon. I don't think there is an issue till now. So clearly this is your xn. What about xn plus 1? So if I just write xn plus 1, xn plus 1 would be summation k equals to 1 to 1 upon k factorial, and here you will have 1 upon 1 minus, instead of n you will have n plus 1, instead of n you will have n plus 1, and here also you will get n plus 1. Now you see, this particular thing is being divided by n, and this particular thing is divided by n plus 1. So clearly this would be more and this would be less. less being subtracted from 1. So clearly, this would be more. I mean, this particular side would be, as compared to this particular thing, this will be more. Because see, here 1 is getting subtracted by k minus 1 upon n. Here 1 is getting subtracted by k minus 1 upon n plus 1. So n plus 1 is greater. Obviously, this would be less. So less is being subtracted from 1. Here, more is getting subtracted from 1. And same applies to all these brackets. So clearly, you can see that this particular thing, xn plus 1 would be greater than xn. Clearly, the sequence xn is an increasing sequence. This particular sequence xn is an increasing sequence. Now, just think about this. Xn is equal to what? It is equals to 1 plus 1 plus 1 plus 1 plus, this summation k equals to 2 to n nck upon into 1 upon n raised to power k. So clearly this is greater than 2. So clearly xn is greater than 2. Now just think about this. Xn is equal to what? Xn is equal to 1 plus 1 plus I think this I will write. This 1 I'll write inside only. So I'll write this way. Summation k equals to 1 to n. 1 upon k factorial was there. And I divided this n inside. So basically I'll use this. Okay, so clearly here if this what this is one, sorry. So basically if I'm not subtracting anything from 1, so that side, so if I write this way, is that not reasonable? Just think about it. Okay, because now here I'm comparing it by 1 upon k factorial. So clearly this is 1 minus something. Here I'm not writing anything. I'm just writing 1 upon k factorial times 1. So here you have this product where you have this 1 being subtracted from something. So obviously this side is less than this side. And just expand this side. So this way I can write that my xn is equals to what? It is equals to 1 plus xn is less than 1 plus summation. Okay. K equals, sorry, again I've written the same. Okay, k equal to 1, and this is 1 upon k factorial. Now you see one of the fundamental inequalities is that if I just want to write n into n minus 1 into n minus 2 dash 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 3 into 2 into 1, this is what? This is n factorial. Obviously, this would be greater than 1 being written here, fine, 2 being written, fine. But if I compare 3 with 2, so obviously 2 would be less than 3. If I compare 4 with 2, obviously 4 would be greater than 2, and so on. If I just compare it with all these multiplications of 2. So I know that this n factorial is always greater than 2 raised to power n minus 1. So if I do the same, if I use the same, so xn can be written less than, because 1 upon k factorial in that case would be less than 1 upon 2 to the power k minus 1. So this would be 1 plus summation 1 k equals to 1 to n, and here you have 2 raised to power k minus 1. Just try to replace this. So this is xn would be less than 1 plus, if you just write here, even as n tends to infinite, this will give you 1 upon 1 minus 1 by 2. So it implies that your xn is less than 3. So xn is an increasing sequence, and xn is bounded from both sides. From on the lower side, it is bounded by 2, and on the upper side, it is bounded by 3. So xn is a bounded sequence. It is an increasing sequence. So by monotone convergence criterion, we can say that xn converges. And where does it converge? So as limit n tends to infinity, we understand that this xn would be equals to 1 plus 1 upon 1 factorial plus 1 upon 2 factorial dash 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 1 upon n factorial. This is equivalent to writing this way. Okay, and clearly this limit is called as E. This is a constant E. Okay, so understand that this particular sequence xn given by 1 plus 1 upon n raised to power n is an increasing sequence, it is a convergent sequence, it is a bounded, obviously, sequence because it is convergent, so it is bounded, and it converges to E. Okay, now let us try to do the same question using some easier methodology, because you see this at times you may not remember binomial theorem, uh, and you may not be that if you're not that skillful in binomial theorem, how to do these questions. So let us just take uh, let us take the help of some other fundamental inequalities like arithmetic mean greater than equal to geometric mean greater than equal to harmonic mean to understand a very important this particular sequence. Okay, so just uh, let us consider two sequences. Let us consider two sequences, let's say an and bn. Okay, and let us say that this an is defined as 1 plus 1 over n raised to power n, and bn given by 1 plus 1 upon n raised to power n plus 1. One observation is very much clear, that this bn sequence would be strictly greater than an for all n belongs to natural. This is very much clear because you know that bn can be written as what? This can be written as 1 plus 1 upon n raised to power n times 1 plus 1 upon n. Clearly, this is greater than 1, and this particular fellow is an. So you can clearly see that this bn is greater than an. Now, we've seen already that this particular sequence is a strictly increasing sequence, but that we saw using, we can say, binomial theorem. Now, let us take an alternative approach and try to prove the same. Try to prove that this is an increasing sequence by taking an alternative approach. And this is a little bit, you can say that easier approach, but it requires you the inequality, this. So one of the classical inequalities is that the arithmetic mean of n positive numbers is greater than geometric mean of n positive numbers is greater than equals to harmonic mean. So basically, if you have n positive numbers, let's say a1, a2, a3, an, then a1 plus a2 plus a3 dash 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 an divided by n, which is the arithmetic mean, is greater than equal to geometric mean, which is the nth root of a1, a2 dash 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 an, and it is greater than equal to the harmonic mean of, which is equals to n upon 1 upon a1 plus 1 upon a2 dash 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 1 upon a. So harmonic mean of n numbers, this is geometric mean of n numbers, this is arithmetic mean of n numbers. So this is one of the fundamental inequalities. Okay, now just try to use this inequality and see how things work. So, and see uh, how briefly we can write the proof. So basically, if I'm saying that, if I'm considering this as an, sorry, 1 plus 1 upon n raised to power n, and let me use this arithmetic mean greater than equal to geometric mean for n terms. So I know that arithmetic mean is greater than equal to only arises if all these numbers are equal. So if all these numbers are not equal, then I will write the stricter inequality. So an plus 1 is greater than gn plus 1. That is, if I want to write, let's say I'll use a1 as simply 1, and all other numbers, that is a2, a3, dash, 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 an plus 1, I'll write it as 1 plus 1 upon n. Okay, now just try to use arithmetic mean. Just try to write the arithmetic mean of all these numbers. So this will be 1 plus, how many numbers are these? These are n numbers, divided by how many totality numbers? So these are n plus 1, would be greater than the geometric mean. Geometric mean is 1 into 1 plus 1 upon n raised to power simply n. So you know, this is n plus 1, this is 2. So totality, these are n numbers here. So n numbers are what? 1 plus 1 by n. So this is 1 plus 1 by n raised to power n. And this whole raised to power 1 upon n plus 1. Because here you had power n because there were n numbers. Here you have n plus 1 numbers. Okay, so this n cancels this, so you have this n here, and this will become, I think, n plus 2 upon n plus 1 is greater than 1 plus 1 upon n raised to power n upon n plus 1. Fine. And the same you can write, this particular thing you can write as 1 plus n plus 1. You can write n plus 2 as n plus 1 plus 1. So basically it is 1 plus 1 upon n plus 1. See clearly, this n plus 2, you can write it as n plus 1 plus 1. So I think you can write this way, and you just take this n plus 1 both sides. This will be like n plus 1, power n plus 1 both sides. This will be this way. So from here, you can clearly write that an plus 1, clearly this an plus 1 is greater than an. So an is strictly increasing sequence. Okay. Now just consider the sequence Bn, which was given by, just consider the sequence Bn given by 1 plus 1 upon n raised to power n plus 1. You know, this was a sequence Bn. If I want to write this sequence Bn, whether it is an increasing sequence or a decreasing sequence, again I use this arithmetic mean greater than geometric mean greater than harmonic mean, but only one part. That is, the geometric mean of n plus 1 numbers is greater than harmonic mean of n plus 1 numbers. And now, because this is n plus 1, so I'll use this. So a1 I'll use as 1, and a2, a3, dash, 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 an plus 1, I will write it as 1 plus 1 upon n minus. Okay. Now just try to write the geometric mean of these numbers. So if I write the geometric mean of these numbers, this would be 1 plus 1 upon n minus 1 raised to power n. So because these in totality are n numbers, raised to power 1 upon n plus 1, because in totality these are n plus 1 numbers. So geometric mean would be this. This geometric mean of n plus 1 number would be greater than the harmonic mean of n plus 1 numbers, these n plus 1 numbers. So what would be harmonic mean? This would be simply n plus 1 divided by 1 plus, in totality, how many numbers are these? These are n numbers. This being, this I can write it as 1 upon, so I'll write 1 upon 1 plus, because whenever we are finding the harmonic mean, the formula is n upon 1 upon a1 plus 1 upon a2 dash, 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 1 upon an. So just let me write 1 upon this thing. So this would be 1 upon, so this will be n minus 1, and this will come as n here. So this would can cancel. Okay, so just think about this. Just think about 1 upon an plus 1. So I'll write 1 upon an right now. Okay, an plus 1 right now. Okay, so this would be 1 upon, and this is equals to 1 upon an also. This is equals to 1 upon a2 also, and so on. So this will be equals to 1 upon n upon n minus 1. Okay, so this would be n minus 1 upon n, and these being added, all these being added, 1 upon a2, 1 upon a3, 1 upon an plus 1. So we can write instead of writing addition, because all these numbers are same. So basically it's equivalent to multiplying them and multiplying this particular thing n times. So this gets cancelled here. So one can clearly see this is 1 plus 1 upon n minus 1 raised to power n is greater than 1 plus, so this gets cancelled, the 1 plus 1 upon n raised to power, sorry, raised to power n plus 1. So clearly you can see that this is what? This is bn minus 1. What is this? This is bn. So one can clearly see that this bn sequence is a decreasing sequence. You saw that an is an increasing sequence and bn is a decreasing sequence. Just I'm giving you a formula, probably we may derive it some other time. Just remember this formula, which suggests that limit n tends to infinity. Probably I may derive it at any future time, but just remember this. This is equals to e raised to power lambda. So both sequences an and bn, both of them limit is equals to e only. However, the sequence an is an increasing sequence. The sequence bn is a decreasing sequence. Okay, this is very much clear. So for bn, this will be the lower bound, that is the greatest of lower bound. For an, this would be the upper bound. So I can write for an would be less than equal to e, or an would be strictly less than e, and bn would be this way. For bn, I can write that, sorry, because e is the lower bound for that. Because, so since if the sequence is decreasing, then it always converges to the greatest of lower bounds. Okay. Okay. Now let us move to one important thing that can be looked at. Just consider a sequence an. Just consider a sequence an. Now let's say, just forget that an. Just consider this as, let's say, capital A, which is given by 1 plus 1 upon 1 factorial plus 1 upon 2 factorial plus 1 upon 3 factorial dash 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 1 upon n factorial. Okay, so consider this particular sequence. We know that if I want to find this limit of this particular sequence, this is equals to e. This is equals to e. However, this e is what? Basically, if I want to write e would be, if I just want to explain what is e is just this particular infinite series. It will go on. And what is an? This. So one of the important results that follows is that e minus an is obviously positive, because e is an infinite sum, an is a finite sum, and all these things are positive only. So e minus an is indeed positive, but it is also bounded on the other side by 1 upon n into n factorial. This is a very important result. Another important result is that this particular fellow, e, is an irrational number. So let us try to see both of them. Let us try to see both of them. But let us first try to find this particular inequality. So our aim is to just prove this inequality and just try to prove that this e, which happens to be the limiting case of this an, is an irrational number. Okay, so let us first concentrate on this particular thing. Understand, this is an is what? Just revise it. I mean, this an is a finite sum. E is an infinite sum. Basically, this is the limiting case of an. Okay, so this particular thing, e minus an, indeed has to be positive, because e, after all, will contain infinite many terms. This an, when subtracted, will get 1 upon n plus 1 factorial, 1 upon n plus 2 factorial, so on and so forth. So basically, it is greater than 0. This is quite evident. But it is less than 1 upon n into n factorial. This needs a certain inspection. So let us inspect this. Okay, so we know that this particular sequence an, if I write this an, this is a Cauchy sequence. This is clearly a Cauchy sequence, because limit an exists and it is equals to e. So a sequence which is convergent in R is Cauchy sequence in R. So basically, this is a Cauchy sequence in R. Okay, since it is Cauchy, so let us try to evaluate what would be an m minus an for all m greater than 0. Let us try to write this. Even if I take a mod, even if I don't take a mod, nothing matters much because I know all these quantities are positive ones, and an plus m would imply that I'm continuing this series to 1 upon m n plus m factorial. So basically, if I do an plus m minus n, certainly it is positive. So I'm not using a modulus thing. If you want to use, you can use that also. This will be equals to what? It will be certainly equals to 1 upon n plus 1 factorial, 1 upon n plus 2 factorial, dash 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 1 upon n plus m factorial. Do remember a n plus m would be what? It will be equals to what? It will be equals to 1 plus 1 upon 1 factorial, dash 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 1 upon n factorial. Then you will get n plus 1 factorial. And this series will go on continuing till n plus m factorial. Now, this particular thing here is a n. So if I subtract a n from a n plus 1, I'll get this remainder thing. So 1 upon n plus 1 factorial, 1 upon n plus 2 factorial, dash, 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 1 upon n plus m factorial. So a n plus m minus of a n will certainly be less than, if I take n factorial common, so what I'll get? I'll get simply 1 upon n plus 1 plus 1 upon n plus 2 into n plus 1. If I think of n plus 3, I'll get n plus 3 into n plus 2. I will get n into n plus 1, and so on and so forth. Here I will get, I think, 1 upon n plus m, n plus m minus 1, dash, 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 n plus m. Okay, now just think about if I just compare it by denominator side, you see n plus 2 is here. So this is equal to, sorry, this is equal to, if I just compare by n plus 1. So basically what I'm going to write, I'm going to just write 1 upon n plus 1. And here also I'm going to write just n plus 1 whole square. Clearly you can see n plus 2. You know that this n plus 2, I'm writing it here somewhere. You know that n plus 2 is greater than n plus 1. So clearly 1 upon n plus 2 would be less than 1 upon n plus 1. So if I replace this n plus 2 by n plus 1, certainly this sign would be there. Okay, this would be 1 upon n plus 1 whole square dash dash 1 upon n plus 1, n plus 1 raised to power n. Okay, so this is one thing. Now, if I even take this, if I keep this n constant, and let me take m towards infinity, let me take m towards infinity, large as possible. So a n plus m minus a n, which would certainly imply what? Because if m tends to infinite, this particular thing will go to e. Okay, because if m tends to infinite, just let me help you here. So if m tends to infinite, this implies that this is going to be an infinite series, right? And this infinite series, this infinite sum is equals to what? This is equals to e. This is something that we've already seen. And we are keeping n as a constant. So this is e minus an only. So your e minus an would be less than 1 upon n factorial. And this would be in, sorry, this would be a, this would be an infinite sum in GP. This would be an infinite sum in GP. So this is 1 upon n plus 1 divided by 1 minus 1 upon n plus 1. Right? So this is a upon 1 minus r. So here, from here, you can clearly see that e minus an would simply be less than 1 upon n into n factorial. So this is one of the most, one of the important inequalities that you should remember, that if I want to evaluate what would be e minus of an, the bounds of it would be on the lower side, it will be bounded by 0, and upper side, it will be bounded by 1 upon n into n factorial. Is that clear? Okay. Now let us just focus our attention towards E. So what is E basically? E is equals to what? E is equal to 1 plus 1 upon 1 factorial plus 1 upon 2 factorial dash 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 1 upon n factorial plus 1 upon n plus 1 factorial. So basically this is an infinite sum. So basically I can write that this particular series E is nothing but it is equal to summation k equals to 1 to n. You can write, and n tends to infinity 1 upon k factorial. Okay, the claim is that this particular number is not a rational number. Rather, it is an irrational number. The claim is that this is an irrational. How to prove this? How to prove this claim? So we'll use it. We'll use a proof by contradiction approach, as we've taken for proving root 2 and root 3 in the very first lecture. Let us try to prove that this is an irrational number. So just an idea I'm giving you. I'm not writing an elaborate proof right now, but just an idea for from there you can develop. Most of the textbooks have solved this particular thing, so I'll leave it to you. But I'm giving you an idea, right? Just an idea. So let us consider that this E is a rational number. Let us consider that this E is a rational number. Let's say it is equals to P upon Q, where P and Q can be reduced to the lowest terms, that is the GCD is equals to 1. GCD of P and Q is equal to 1. And here, let's say P belongs to set of natural numbers. Q also belongs to set of natural numbers. And let us consider that this E is a rational number, sorry. So by rational number, I mean it can be expressed in form of P by Q. Now, if it is a rational number, then just let me write. Now just think about this. If E is a rational number, which can be written in the form of P by Q, which can be written in the form of P by Q, okay? If I multiply Q factorial both sides, so this particular thing would be a integer. Is that clear? This would be an integer, clearly. See, if I multiply this Q factorial times, so basically Q factorial times E, this Q gets cancelled. You'll have Q minus 1 factorial times E. E is what? P upon Q. So if it is P upon Q, so Q cancels Q. So you will have P into Q minus 1 factorial. So basically this is equal to what? This is equal to P times Q minus 1 factorial. Indeed, it is an integer. And here also, if Q factorial is multiplied to 1 plus 1 upon 2 factorial dash dash 1 upon Q factorial plus, so this is also an integer. Clearly, you can see on your own. Okay, see, this 1 into Q factorial, this is integer 1 upon 2 factorial. So Q factorial would contain 2 factorial. So 2 factorial gets cancelled, cancels 2 factorial. So remaining all the terms are product of integers only. And same thing can be applied to each of these cases. Now, what about this? If I multiply this Q factorial. So if I multiply Q factorial, I'll get 1 upon Q plus 1 here. I'll get 1 upon Q plus 2 into Q plus 1 here. I will get 1 upon Q plus 3 into Q plus 2 into Q plus 1, and so on and so forth. Clearly, I can use the inequality I used just above, that this would be less than 1 upon Q plus 1 plus 1 upon Q plus 1 whole square, 1 upon Q plus 1 whole cube, and so on and so forth. And if since this is an infinite series, this will go on progressing. So I can write this is less than this particular thing, this particular fellow, this particular bracket is less than this. And if I just take an infinite sum from here, so I know that this would be equal to 1 upon Q plus 1 upon 1 minus 1 upon Q plus 1. So basically, it will be less than 1 upon Q. And 1 upon Q, if Q is an integer, even if I take if q is a natural number, even if I take q to be 1, then also it suggests that this is less than 1. And if a positive quantity is there and this is less than 1, it implies that this particular bracket lies between 0 and 1. So certainly this is not an integer. So here you, on the left hand side, you have an integer. On right hand side, you have integer plus something which lies between 0 and 1. So this is basically in a fraction. Basically, this is in fraction. So clearly, integer can never be equals to integer plus something lying between 0 and 1. So clearly, we arrive at a contradiction that E cannot be expressed in the form of P upon Q. So clearly, E is not a rational. Okay, now let us try to do two important limits. And these are very difficult limits to evaluate at the very first instance. But having this background, probably now you'll be able to figure out how to find these two inequalities. So without wasting time, let us try to evaluate one of the important limit. And here it is. Try to find the limit n tends to infinity n times sine of n times 2 pi n factorial e. We want to find this limit. And how to find this limit? See, understand that sine is a continuous function. And just I'm writing it. If you are not aware, then it's fine. But if you're aware, then it's good. That if xn tends to x, then f of xn tends towards f of x. That is, I can write that limit f of xn is equal to f of limit xn here. This is something that we can do for continuous function, since f is a continuous function. Okay. Now instead of writing, okay, one thing I'll do. See, what is E after all? E is 1 plus 1 upon 2 factorial plus 1 upon 3 factorial dash 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 1 upon n factorial. And let us write all those things that we wrote above as the remainder term Rn. And what is E? E is after all this Rn tending to its infinity. So what I can do, I can say that if I'm writing this series with the condition that limit Rn tends to infinity, and remember this is what your An was, plus Rn, this is equals to E. This is equals to E. So if Rn tends to infinity, this particular thing is equals to E. I hope it is clear. And see, just pay attention. We already know that this Rn would certainly be greater than 1 upon n plus 1 factorial. Because see, what is Rn? Rn after all inculcates 1 upon n plus 1 factorial plus 1 upon n plus 2 factorial and so on and so forth. So clearly Rn is greater than 1 upon n plus 1 factorial. Okay. And on the other side, if you just think about this, what is your Rn? If you just think what is n factorial Rn, so n factorial Rn, I can write that n factorial Rn would certainly be greater than 1 upon n plus 1. And n factorial Rn is equals to what? It is equals to n factorial divided by n plus 1 factorial, n factorial divided by n plus 2 factorial, dash dash dash. Certainly, this n factorial Rn would be less than 1 upon n plus 1. This is fine, but here you see the same technique that we used if I write infinite times. Because see, n factorial cancelling n plus 2 factorial will give you n plus 2 into n plus 1. So again, using the same, I can write this. So that way, if I just think what would be the upper bound of n factorial Rn, so n factorial Rn can be written less than 1 upon n plus 1 upon 1 minus 1 upon n plus 1. Clearly, this is 1 upon n. So one can write that your n factorial Rn always lies between sorry, 1 upon n plus 1 to 1 upon n. And if I want to take this limit, n tends to infinity, n factorial Rn, so from Sandwich theorem, this would be equal to 0. So sorry. So n factorial Rn limit n tends to infinity would give you 0. Now we'll use this. We'll use this. So we want to find the limit. Again, the question was this. We want to find the limit n tends to infinity n times sine of n times 2 pi n factorial e. See, I understand that as n tends to infinity, as Rn tends to infinity, sorry, as n tends to infinity, that is as Rn tends to infinity, your so as Rn tends to infinity, your e comes out. So basically, if I write this e is nothing but it is equals to limit Rn tends to infinity 1 plus 1 upon 2 plus 1 upon 3 dash 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 1 upon n factorial plus Rn. So basically, this is equal to e. So instead of e, I can write it as limit Rn tends to infinity. So basically, instead of writing this, what I'll do, I'll write limit n tends to infinity, n times sine n times 2 pi n factorial. Instead of e, I'll simply write Rn because the limiting case Rn tends to infinity is equals to e. And this I can only do because sine is a continuous function. This is something that I've already stated as a fact. We'll do it later on when we'll do the continuous functions. Okay, now just pay attention to this. We know that n factorial Rn tends to 0. And we know one of the limits that theta tends to 0, sine theta upon theta can be written as 1. So that requires a little bit of manipulation. So what I'll do, I'll just use this manipulation that is n. I will write sine n into 2 pi n factorial Rn. And same way, I'll simply write here n into 2 pi n factorial Rn. So if I have written this, so I will have to okay, this n was not there. I'm so sorry. I'm so sorry. This n was not there. That is why I was getting this n is not there. So sorry about it. If I have written somewhere, please correct it. I think this n is not there. So sorry about it. Okay, so sorry. So sorry. So sorry. Okay, so the question is sine into 2 pi n factorial e. Okay, so this question is sine of 2 pi n factorial e. So sorry about it. Just correct it. So basically this n is not here. So n times sine of 2 pi n factorial e. Instead of e, I have written Rn. Rn tending to infinity would give you e. And so seeing this 2 pi n factorial Rn, I'll divide it by 2 pi n factorial Rn and I'll multiply this. So I'll multiply this by 2 pi n factorial Rn. Now this particular thing will go towards 1 because I know that n factorial times Rn, n factorial times Rn tends to 0 as n tends to infinity. So this is completely equals to what? This is completely equals to 0, and this is like sine theta upon theta. Now I'm left with something this. And why I'm not able to make my mind? Because here n is tending to infinity. This n factorial Rn tends towards what? This n factorial Rn tends towards 0. So this is infinite into 0 kind of form. So just little bit of attention is required here. See, I've already written that n factorial Rn is always greater than n plus 1 and is less than 1 upon n. So what I'll do, I'll multiply 2 pi n on both sides. So 2 pi n into n factorial Rn would be less than 2 pi. And here you will get 2 pi n upon n plus 1. As n tends to infinity, I know that this particular limit 2 pi n times n factorial Rn is equals to 2 pi. Clearly, this entire limit will come out as 2 pi. That is, if I want to write limit n tends to infinity, n times sine of 2 pi n factorial e, this will turn out to be equals to 2 pi. So this is an important question that you should remember. Now let us just do one of the questions in the similar lines, and then we'll conclude this lecture. Instead of sine, if I give you cosine, and if I give you this limit to evaluate, what would you think the answer would be? What do you think the answer would be? So I'm giving you a sequence, or you can say just a limit question. Let's say I want to give you this. So you can take it as a question or a problem. So consider a sequence Pn, which is given by cos of 2 times n factorial e pi. What do you think limit Pn would be? What do you think limit Pn would be? Okay, now just think about if you don't remember what all I have done, if you just want to do it in an easier fashion, see, I know what is E. E is equals to 1 plus 1 upon 1 factorial plus 1 upon 2 factorial dash 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 1 upon 3 factorial, sorry, 1 upon n factorial here, plus 1 upon n plus 1 factorial plus 1 upon n plus 2 factorial and dash 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 will continue. Now see, if I multiply 2 times n factorial times e, I know that this would be equivalent to 2 times n factorial 1 plus 1 upon 1 factorial plus 1 upon 2 factorial dash 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 1 upon n factorial dash 2 times n factorial, and here you have this 1 upon n plus 1 factorial plus 1 upon n plus 2 factorial, so on and so forth. Now just think about this. Is it not an even multiple of integer? See, this if n factorial multiplies with this is an even integer, right? This is an even integer. This is an even integer. I'll write it as some nn. Okay, this is an even integer plus some remainder term. So let's say I'll write it as del n. I've already stated, and we've already seen that this del n, because see, this is greater than, obviously this particular thing is greater than 1 upon n plus 2 n plus 1 factorial, n factorial gets cancelled. So this is greater than 1 upon n plus 1, and this 2 also accompanies, and it is less than 2 upon n. This is something that we have already seen. The same steps. Okay, so from here it is clear that limit del n would be equal to what? 0. Limit del n would be equal to what? 0 by scientist. Now let us pay attention to this. So what was asked? Asked was limit cos of 2 times n factorial e pi. This is what was asked, right? Just pay attention to question. Pay attention to the question. Okay. Now, if this is the case, having written 2n factorial e, so this 2n factorial e is equals to what? This is equal to limit n tends to infinity cos of nn plus del n times pi, right? This is how it is. Understand that this nn is an even integer. This is an even integer. So it is equivalent to writing limit n tends to infinity cos of nn pi, this is even multiple of pi, plus del n pi. So you know that this cos of 2n pi plus theta is simply equals to cos of theta. So this will give you what? This will give you limit n tends to infinity cos of del n pi. And we know that as n tends to infinity, this del n tends to 0. Since this del n tends to 0, so this is cos 0, and cos 0 is simply 1. So the limit Pn that was asked in this question that I gave you is equals to. So I hope I am able to explain you all these things. We'll see more interesting questions and discussions on sequences to follow. Till then, take care. Bye-bye. Keep revising whatever has been taught so far. I hope to meet you in the next lecture. Thank you.